Hey everybody, I'm Chili. Welcome back to 3D Fundamentals Tutorial 9. Today I got a doozy for you because we are going to be incorporating our first shader unit into our pipeline here. And the one we're going to start with is the pixel shader. We're going to start with the fun stuff. Pixel shader, in my opinion, is the most interesting shader to work with, the most important shader to work with. And the reason why is because it is the thing that determines the colors of all the pixels on the screen, so it is the thing that ultimately determines your image. Now, you might be wondering, well, Chili, I've heard a lot about this pixel shader bullshit, but what is it anyways? So let's take a look at our pipeline diagram here. And specifically, you want to look at the end of it. So you've got the triangle rasterizer unit here, and that corresponds to the draw triangle function in our pipeline class. And it is being called from the perspective screen transformer, which corresponds to post-process triangle. So post-process triangle processes the vertices, then it passes that triangle onto draw triangle. What draw triangle does is it scans over the entire triangle in screen space and calls put pixel with some determined colors. Now the determination of the colors here is fixed, right? It is generally doing a texture lookup. But I mean, obviously that's not the only way that we want to draw triangles ever. We want to draw triangles in a whole bunch of different ways. So what we want to do is we want to make this color determination process here, we want to make it configurable. And the way we're going to do that is in code, we're going to use basically a functor and templating, but we'll get into that later. But in general, what we want to be doing here is we want to have a piece of code that we can plug in here, and that code will determine the color of the pixel based on its input. So turning our attention to the code here in the pipeline, you got post-process triangle vertices, calls draw triangle does a bunch of bullshit, calls a bunch of things, and here is the ultimate drawer of the triangle, draw flat triangle. And here is where we are determining the color of the pixel. So we basically want to replace this stuff here with a call to a shader object. Because if you think of the case of drawing a textured triangle with clamping as opposed to drawing it with wrapping, or even drawing just a flat color, the only part that really has to change is this. All this stuff can remain the same and it'll work. So we just need a way of being able to configure this part of our code. So if we take a look at the commits here I implemented the programmable pixel shader stage in the pipeline, and I've added the first effect. So let's take a look at how the pipeline changes when we add the programmable pixel shader stage in there. So first thing, obviously I'm going to change a little bit of comments here. Now it is saying drawing triangle pipeline with programmable pixel shading stage. Now the main thing here is we are now causing pipeline to be a template class, and we are templating it on an effect. So now the pipeline will be basically configured based on an effect class that we will define outside of the pipeline class. And now, instead of defining a single vertex class in the pipeline, the vertex format is going to change depending on what effect we're using. Different effects have different requirements. Textured effects require texture coordinates, but untextured effects don't require those, etc. So instead of hard coding the vertex type in the pipeline, all we do is we type def effect vertex as vertex in the pipeline here. So the effect will define the type of vertex that it uses. That's the first part. And then we just delete all of that vertex code. Now I'm also removing bind texture because texture is specific to the pixel shader effect, right? If an effect doesn't have a texture, obviously bind texture is going to make sense. And the texture is going to be stored in the effect, in the pixel shader, not in the pipeline here. So bind texture doesn't make any sense. We delete that shit. And then down here, all this stuff is the same, right? And you would expect that because pixel shader only affects the rasterization at the very end of triangle drawing. And here we go. So before, what we had here was we had texture lookup, we had clamping, all that good stuff, scaling by the screen dimensions. or texture dimensions, I guess. And we replace all that with just effect.ps. That's a pixel shading object. And then we call the function operator on that object, and we pass it the interpolated vertex data. So we interpolate vertex data as normal, and then we pass it to the pixel shader, and the pixel shader will take that data and determine a color based on its input interpolated data. It'll return that color, and that is what we put on the screen. So now the pipeline will have an effect object. We removed the texture from there, but we now have an effect object, and that the effect is going to hold all of our shaders. Right now we only have pixel shader, but later on we're going to have other kinds of shaders, and they are all going to be embedded in the effect. So the effect object contains a bunch of shader objects, and the shader objects are all just basically functors. So let's take a look at an effect class, shall we? The first one is a texture effect. That's what we're creating. And here is the vertex, which is the same vertex we had before in the pipeline, just has a position and texture. But now we are defining it in our texture effect class. And here we have the pixel shader class. This is the functor. It has its function operator. This is what is going to be called to do the actual shading, and it does the texture lookup just like we had before. There's no change there. We also got the bind texture function, and all that does is it loads a texture, and then it just calculates, or it stores the width, the height, and the clamping that is used in here to do the texture clamping. So we store that, we only calculate it once when we're loading the texture, and then we just refer to it as member variables. And of course we got the unique pointer for our texture here. And that is the pixel shader class. And then in the texture effect, we just embed a pixel shader object. Pixel shader doesn't have a constructor, or it just only has a default constructor, so we don't have to do any construction shenanigans for effect. All we do is we embed the pixel shader, and it's created when the effect is created. And that's it. It's that goddamn simple. And by the magic of templates, we can just put this in our pipeline, and it works. Put this in your pipe and smoke it, my friends. So how do we put it all together? Well, let's take a look at the new and improved cube skin scene. I can never say that correctly. So we add a new type def. We are type defining pipeline, which is templated on texture effect as just pipeline. And then we type define pipeline vertex as vertex. So I like to use these type defs. It makes my code a little sexier here. And the main change here is going to be, instead of calling pipeline bind texture with a file name, we call pipeline.effect.pixelshader.bind texture. So we bind a texture to the pixel shader. So yeah, it's all the same after that. This is really the only change we had to make in order to use our texture effect in the pipeline. And if you run that shit, you see that it is the same as before. Nothing changed. It still runs pretty much exactly the same. Only now our shit is configurable. So let's take advantage of our configurable shit. Let's make another fucking effect. So the next effect I added, and I'll just hit tab here, is the color blend effect. So here we give each vertex its own color. And as we are drawing a triangle, we blend between the colors of the different vertices. And this is what you get, the color blend effect from vertices. And this is implemented in the pixel shader. So how do we do that? So to start off, let's take a look at vertex color effect, because that is where all the actions are happening. This is where it is determined how the effect works. So again, we define a vertex. This vertex is going to be different than the vertex for the texture effect, because now we're not going to have a texture, so we're not going to have texture coordinates, but we are going to have a color per vertex. So we're going to have a color member. Now you might be noticing something. You might be saying, Chili, this is weird. It says color, but it's a vec3. What's up? This effect here is going to be blending colors between vertices, so it has to interpolate the color member. Now, interpolation doesn't really work too well for ints. It's much easier to do interpolation math with floating point values. So we're going to encode our vertex colors as floating point, because remember, a color is just a collection of three numbers, red, green, and blue, right? Doesn't matter whether those numbers are unsigned char or whether they're int or whether they're float or double. No, it actually doesn't matter at all. So we encode this as a vec3, and the way I'm going to encode it is basically the same as for normal color. 255 is full channel, 0 is none of that channel. So 255, 255, 255 is white, 000 is black. And this is a little different. I mean, in hardware, generally color is also dealt with as floating point numbers. That's one of the first things you realize when you start doing, shaders in Direct 3D. Color is float until the very end when it is converted out into int and drawn to the surface. So that's the same, but in hardware, generally color is normalized. So 1 is full, 0 is nothing. But here we're using 255 because that makes it easier to convert. So yeah, that is our vertex type. And the pixel shader itself couldn't be simpler, because all we're doing is we're taking the interpolated input vertex and we are converting that to an integer color. And the reason why we can do this is because in colors.h here, I include vec3 and I've added a couple of conversion operators. So a converting constructor and a conversion operator to convert from color to vec3 and from vec3 to color. And this is just going to make our life easier, a little bit of syntactic sugar there. And yeah, that's the whole effect, because this pixel shader doesn't have any texture or anything, doesn't need any bind function, doesn't need any member variables, no constructor, just a very simple functor gets the job done. Now I made a little change to pipeline. There shouldn't normally need to be a change, but I must have had to fix something. And what I had to fix was before, what we were doing was when we transformed the vertices to create the output stream, we were applying the transformation to the position and just copying the texture member. But here, fuck off. Here, as you notice, we don't have a texture member anymore. So depending on the effect, some effects aren't going to have a member T. So this code is bad. What we want to do is we want to touch the position. This is really pissing me off. We want to transform the position, but leave the rest of the vertex alone. And the way we do that is we use a constructor of the vertex that allows us to set the position, and it will copy the rest of the vertex members as they are. And this allows this module to only touch the position and not have to know anything about the rest of the members. So that constructor is here. It takes position and it takes a vertex, which is the source from which you copy all of the other members. So here we set the position from the passed in position, but we set the color from the copy source color. And it is that constructor that allows this code to work without having to know what the other members are. Because remember, we're passing in template. This code doesn't exactly know what members vertices has, right? It doesn't know what members it has. It only assumes that it has a position. That's the only thing it assumes. Everything else it doesn't know. So it has to allow that type to copy its members itself. Now in cube.h, we add another getter to generate a different kind of cube. This is a plane cube. Plane cube only has 8 vertices, the minimum required, and it's mapping them accordingly. Whereas the skin has more vertices because it has to do that whole, skinning with the unfolded texture. It has to make some vertices independent of other ones, even though they're in the same space. For texturing purposes. But this one doesn't have that requirement, so we can use the minimum amount of vertices. And there you go. That is all the stuff that was required. The actual demo scene here, it creates the index triangle list, cube, get plane, template that on vertex. And here, because get plane only sets the positions, you've got to set the other stuff yourself. So here we set the colors of the 8 vertices. And the rest of this stuff is going to be the same, and that's all the same. And you do that, and you get this effect here. And it looks pretty cool. It's not bad. Not bad. Pretty standard effect when you're learning about shaders. Now, the final effect I'm going to show today is basic solid color effect. And you might think that this one is the simplest of all, but actually it's a little more complicated. So imagine you've got a cube like this, you've got 8 vertices. You want to give each face its own color. How do you do that? Well, you're going to have to store those colors somewhere, right? Where are you going to store them? Generally, you store your drawing information in the vertices. So, okay, well, I mean, these 2 triangles here, let's just take a look at this triangle. It is going to be yellow. 'Cause you are all yellow. So, all we have to do to make it yellow is, well, with our previous color vertex, if we make these 3 vertices yellow here, and we make this one yellow as well, then it will interpolate between them. They're all the same, and it will draw this yellow. That's great. It'll draw that yellow. Except, what about this fucking vertex? What about this triangle here now? It's got 2 vertices that are yellow. Even if we make this one red, it is going to be also mostly yellow. And that's terrible, right? We don't want that. So, well, let's make this one, let's make it red then. Oh, fuck, now this guy's red, but we wanted this one yellow. Shit, guess you can't do it. And you can't really do it like this if they're all sharing vertices. It's not going to work for you that well. So what you do is you split these vertices up. You make them independent. So now these faces, they aren't going to share vertices with each other. The 2 triangles of the face here, they can share these vertices, that's fine, but separate faces will not share any vertices with any other face. This will increase the size of your model. It'll increase the number of vertices, but it will allow us now to give, these guys all red, and then we can give these guys all green, and then it'll just work. And this would work with our previous interpolating shader as well. But when you think about it, do we really need to interpolate this color component? Because, I mean, it's all going to be one color. Why even interpolate it? So let's create a new shader effect that doesn't interpolate and gets a little speed boost. So here we have solid effect.h. Its vertex is going to have a vec3 for position and a color for color, not a vec3. And the reason for this is if you look through the vertex here, you can see that all the operations here, the addition, the subtraction, they're only affecting the position. So none of these operations will affect the color. The color will remain the same throughout interpolation because it doesn't need to be interpolated. It's the same for all the vertices on the triangle. You'll never have a triangle where one of the vertices has a different color, so there's no sense in interpolating. So don't interpolate it, and when you get the input from the pixel shader, it's just going to be the input from one of the vertices, and they're all the same, so it doesn't matter for the color anyways, and then you just draw that color out directly. No need to even convert it from float to int. And there you go, there's a pixel shader. Now for this, the main work here is going to be done in cube.h because we're going to have a different generator. Generate plain independent faces. So this one generates it with independent faces, meaning there's a lot more vertices. You're going to have 24 vertices, I believe. Some are going to be duplicates, right? Because they have to be independent. And this is going to be, the same. The indices are going to be different, obviously, because we've got more vertices now. And then in your cube solid scene, what have we got here? Well, we're going to pipeline. We're going to template that on solid effect, obviously. In here, I have created an array of colors, and then I just do a loop and assign those colors to the vertex. And what I've done here, so every 4 vertices are going to have the same color. So this is 0, 1, 2, 3, they all have red, and then 4, 5, 6, 7 are all going to have green. So that's the reason for the division in here. And the keyboard input is the same, and this stuff is all still the same. This stuff is all still the same. And there you go, you've got your solid effect. Looks pretty sweet. And the code is sexy as fuck, if I do say so myself. And there you go, there's the idea of a pixel shader in a nutshell. And there is our pixel shader implemented. Now, you can probably imagine here, I've only scratched the surface of what you can do with a pixel shader. The sky is the limit. So I encourage you to experiment with this, come up with your own ideas, make some crazy shader effects, And if you come up with something cool, you know, you can message me on Twitter, on Discord, make a forum post an image of what you made, and I'd like to see that. Maybe I'll even feature it in a future video. Now, one last thing I'd like to say here is, again, I'm making this whole pipeline, this programmable pipeline, we're building it with the hopes of learning how 3D graphics hardware actually accomplishes its goals so that we'll be better hardware 3D programmers. And so I'm modeling it fairly similar to how it actually works in, you know, like an API like Direct3D or OpenGL. But there are some differences. I just like to go over a few of the differences. I mean, first of all, our whole pipeline is templated, right? So that means that if we want to change the pixel shader, we want to change the vertex shader, we want to change the effect, we've basically got to create a whole new pipeline. And obviously that's not how it works in Direct3D. If you want to change a pixel shader, you just bind a different shader. If you want to change vertex shader, you just bind a different shader. Whereas with us, we've got to create a different pipeline for every different effect. This is an advantage for us in that using templates allows the compiler to optimize the code better, to inline the code more aggressively. But the downside is obviously we can't switch things out at runtime. We've got to create a different pipeline for every different effect that we want to use for rendering. But again, working with actual hardware with Direct3D, you can bind different shaders to the same pipeline dynamically at runtime. Another difference is for our shaders here, for example, if we've got a texturing shader, the pixel shader object is going to contain the texture, right? And is going to use its own custom code to access the texture. But with a real hardware pipeline, what you're going to have is an object in your pipeline separate from the shader, and it's a fixed object and it's a texturing unit, and you will bind textures to slots in your pipeline that the texture unit will read, and you will interface with the texture unit. So for example, if we look into the framework in the actual Direct3D pixel shader here, what you're doing is you're setting up a texture object and a sampler state. Sampler state basically represents the texturing engine that is going to be sampling from the texture, and the texture is the resource that is bound to the pipeline. So the sampler represents the texture, and then when you want to read from the texture, you go texture.sample, you pass in the sampler, and you pass in the texture coordinate. But obviously don't worry about this bullshit. We'll get into this when we get into hardware 3D. And that's about it for this video. Thanks for watching. Hope you liked the video. If you did, please click the like button. It helps a lot. And I will see you soon with some more 3D fundamentals.